Okay. So our speaker today is Dr. Levin from University of Wisconsin-Madison. So Dr. Levin got his bachelor's degree in linguistics and psychology. And after spending some time in industry, he came back to academia and got a PhD degree in computer science at Johns Hopkins University. And then he did a postdoc at the Department of Statistics of the University of Michigan. So his research focuses on network analysis, clustering, with application to neurosciences and of course language processing. So today he's going to talk about how to estimate the network mediated causal effects. Please join me in welcoming him.
Thanks, everyone. Thank you all for coming. Thank you, Chuan, for that lovely introduction. And thank you to the seminar committee for the invitation. It's my pleasure to be here. I've been wanting to come and visit College Station basically since I started my professorship, but I started during the pandemic, so it wasn't really an option. So it's really great to be here and see a number of familiar faces from just before the pandemic. Without further ado, let me dive in here. So I want to talk today about a problem that actually I started working on before I went on the job market in I guess maybe it was the summer of 2019. And I was working with my office mate at the time, Mark Fredrickson, who's at University of Michigan. This kind of we started working on this project and we both got very busy with job market stuff. We set it aside. I started at University of Michigan, excuse me, at University of Wisconsin, and was approached by Alex Hayes, who is now a co-advisee of mine, along with Carl Rowe. Alex was looking for a project. He saw this project in my file drawer, so to speak. No one has file drawers anymore. Like you have a text file on your computer, but you know what I mean, right? And so Alex picked up this project and turned it into something really fantastic that I'm excited to share with you. And so I want to preface all of this by saying that everything you see here, credit goes to Alex. Alex is a fantastic student. He's a fifth-year PhD student in our department, and at the risk of shameless, well, not self-promotion, shameless promotion, Alex will be looking for a postdoc starting not this coming fall, but in the fall of 2024. So if you're looking for a good postdoc, keep him in mind. He'll be at a few of the conferences this summer, including JSM. So if you run into him, he's a lovely human being. Have a chat with him. Okay, second thing I should mention. This talk is half about networks and half about causal inference. My training is in networks, so I think about how to model and analyze network data. I am decidedly not a causal inference expert, right? And so there are causal inference experts in the room, and I want to apologize in advance for all the mistakes I make in their field. Please, grant me some lenience for the fact that I'm still kind of a newcomer to some of this methodology. My co-authors are experts in causal inference, and so I may, depending on your questions, defer to them, right? If there's something you ask and I don't have an answer, I'm not one to stand up here and pretend to know something I don't. I will defer to them. I'm happy to get you in contact with either Alex or Mark. They're both wonderful human beings and great collaborators. Okay, enough preamble. Let's get to it. So this is a talk that's partly about networks. So what are networks? Networks or graphs, I'll kind of use the two terms interchangeably today, are data that encode relations among entities. And so we might have a collection of objects or entities out there in the world, and certain pairs of those entities may interact. Okay, we represent these entities as vertices, right? And we usually draw a network by representing the vertices as dots. Okay, and then certain pairs of vertices, certain pairs of these objects interact in some way. And for those pairs of interacting objects, we'll draw a line between them. We say that those two vertices form an edge. Okay, so this picture at the left, right, represents a graph or a network on 5 vertices, yellow, orange, purple, blue, and teal. Certain pairs of them form edges. For example, yellow and teal here form an edge. Certain other pairs of vertices don't form edges. For example, yellow and purple do not form an edge. There's no line between them. Okay, so this dots with lines between them picture is, I suppose, sort of pretty, but not very convenient to work with mathematically. Notationally, it's a lot easier to talk about the adjacency matrix of a network. Throughout this talk, I'll denote that by A, and this is a matrix whose rows and columns are indexed by the vertices in our network. Okay, so looking at our example network here, right, we have 5 vertices, and so we can form a matrix whose rows and columns are indexed by those vertices. And for example, if we look at, say, yellow and teal here. We go to the yellow comma teal entry of this network. We see a 1 there, encoding the fact that these two vertices form an edge, right? On the other hand, for example, yellow and purple do not form an edge. We go to the yellow comma purple entry of this matrix. We see a 0, encoding the fact that they don't form an edge. Okay. So networks arise all throughout the sciences. I'll mention just a couple of places where they arise naturally. Probably most familiar to most of us are in social networks, such as Facebook or Twitter, right? We might like to represent the Facebook social network by representing each user as a vertex. Okay. And pairs of users who are friends, we might draw an edge between them. Okay. Right. Near and dear to my own heart, in neuroscience, networks arise naturally to represent the connectome, meaning basically the wiring diagram of the brain. There, vertices represent usually brain regions, like chunks of the brain, and edges encode which pairs of brain regions interact closely. Okay, you could even represent individual neurons by vertices and encode with edges which pairs of vertices form synapses with one another. Okay, one other thing I'll mention here. So here I've drawn a network that is symmetric, right? Meaning the relation between, say, teal and orange here doesn't have a directedness to it. We can extend this notion to what are called directed graphs, right? Where, think about, for example, Twitter, right? I might follow Jesus on Twitter. Jesus need not follow me back. So sad. Okay. I'm not on Twitter, so, whatever. Right, there's a directedness to the Twitter graph, right? User A might follow user B might follow user A, but neither one implies the other necessarily, okay? Furthermore, we can have weighted networks, right? We might like to encode the strength of an association between two vertices, right? You're closer friends with some people than others, right? You might like to draw a social network that captures that fact. For the sake of simplicity and concreteness today, I'm going to just think about this nice symmetric binary situation, right? But I do want to stress that everything I'm going to talk about can be extended to directedness and weighted networks very straightforwardly. In fact, one of my illustrations at the end, if we have time, will show just that. Okay, but throughout this talk, just for ease of cognitive load, this adjacency matrix is going to be a symmetric binary matrix. Okay, so to motivate what we're going to talk about today, I'm going to work with this sociology study from 1996 called the Teenage Friends and Lifestyle Study. This study followed a group of students in Glasgow, Scotland, over 2 years, starting from age 13. So basically think like United States middle school, approximately. Okay. So this followed 129 students. Each of the students reported who their friends were. So each student was asked kind of like, list your friends, which is a socially very fraught exercise, I suppose, but they dealt with it. And from that self-reported friendship, the authors constructed a social network. In addition to the social network, the authors also collected some auxiliary data about things like spending money, something like allowance money, leisure activities, what kind of music the students liked, that kind of stuff, some additional demographic data, and then some data about students' behaviors, things like alcohol, cannabis, and tobacco use. So one question you might like to answer would be things like, how did these individual observations about things like spending money or leisure activities predict predilection to use, say, tobacco? Okay, so for the sake of concreteness, let's ask a question today. How does the possession or lack of spending money influence students' tobacco use? Okay, so students are given, some allowance money, or perhaps not, by their parents, and you might think that having or not having spending money can influence your decision to use tobacco in at least 2 different ways. One way is a kind of direct effect of spending money on tobacco, right? If I have more allowance money, that's more money I can use to go to the corner store and buy cigarettes. If I'm an enterprising 13-year-old, it was a different time. Okay, so there's a direct effect, right? More spending money perhaps leads to more cigarettes just because you have more money to buy cigarettes with, perhaps. Okay. There's also an indirect effect of spending money on smoking, right? If you and I have similar amounts of allowance money to burn, we are perhaps more likely to be friends, right? And people who are friends tend to, influence one another, right? So we've all heard about peer pressure, right? So perhaps students who are given similar amounts of spending money are more likely to become friends, right? And then if one of those students picks up smoking, that student is more likely to exert peer pressure on another student. Okay, and that other student in turn picks up smoking. Don't smoke. Okay, so to answer questions like this, right, to decouple these two different ways that spending money might influence alcohol, it's helpful to use this causal inference framework. And so for a couple of slides, I want us to all forget about networks. We don't actually, because we're going to use them later in the talk. But let's think about how we'd solve this problem in the kind of simpler regime where this mediator, this in-between structure, which was sort of our network, right? This network, social network, could kind of influence how spending money influences tobacco, right? So we're going to work to think about this under the Niemann-Rubin potential outcomes framework, and I'll talk about that in just a moment. But to set things up, let's imagine we have some confounder variables C. Okay, and so think of these as something like the demographic data that we know about our students in the study. We have a treatment, which I'll assume to be binary, T. This is, say, maybe you got allowance money or not. And we'll talk about that binarizing operation later on. Right? So there's a treatment that might be applied. You either receive the treatment or you don't, okay, indicated by this binary variable. Okay. We have a mediator variable M. Right? In our kind of running example, this is going to correspond to network structure, but for now, think of this as just any old thing you might measure. Right? Forget about networks, just some other set of variables. Okay. And then we have an outcome Y, which corresponds to whatever behavior we're interested in. In this case, Y might be an indicator saying, are you a smoker or not? Okay. Now, I've drawn a graph here, a directed graph, and at risk of introducing some confusion, right? This kind of graph and the social network I showed are essentially unrelated, right? They encode two very different things. So this is an example of what's called a causal DAG, a causal directed acyclic graph. It is designed to encode the causal relations between these variables. Okay, so an arrow from one variable to another means that the first variable causally influences the second one. Okay. So for example, go ahead.
So there is this assumption equivalent for it.
Yes.
And it assumes, let's say, that if I give treatment, me, if he belongs me, and another person, they don't influence each other. But based on your example, it's violated, right? So you assume this assumption is violated?
No, and I'll talk about that in a minute. So the question was about the SUTPA assumption, the stable unit treatment value assumption. And there are situations where you might worry that a network structure causes you to violate this assumption. This assumption basically boils down to saying, like, if I give you a treatment, that treatment doesn't change the behavior of your friends. Okay? I will explain to you how we avoid that here in a couple of slides, I think like 2 slides. Now, there's a philosophical question which I am not going to answer, which is like, is that assumption true about any particular data set? That's, I'm a statistician first and a practitioner. Well, not at all. I'm not a sociologist, right? I work with sociologists. So there's a discussion to be had about whether these assumptions are valid, right? And those really boil down to like, do you believe these assumptions or not, right? There's some kind of, checking you can do. But I'll address specifically like, why is it that those assumptions are not violated here in a couple of slides. Okay, like there's a separate question of like, do you believe those assumptions in the first place? Which we can talk about that maybe over beers, but right. Great, okay. All right, so what are we interested in here? Well, classically, what we try to do is estimate this quantity called the average treatment effect, the ATE. And roughly speaking, it corresponds to what would happen on average if everyone received a treatment instead of not receiving a treatment. Okay, now this quantity is defined in terms of counterfactual outcomes, right? So this Y parens notation says this is the value of our the value that our outcome Y would take in the imaginary world where we applied a treatment. Okay? And similarly, we can define the value that Y would take in the imaginary world where we don't receive a treatment. Okay, so these variables y of 1 and y of 0 are in a sense different versions of this variable y. Okay, and they correspond, roughly speaking, again to kind of called potential outcomes. Right, but they correspond to kind of what would happen if we artificially set treatment to 0 or 1. Okay. And we can decompose the average treatment effect into two terms called the natural direct effect and the natural indirect effect. That corresponds precisely to the direct effect of T on Y. So our treatment can causally influence Y directly. Right? So in our running example, this was the way that having more spending money makes you more likely to buy cigarettes. Okay? But there's also an indirect effect of T on Y. Treatment or not may influence a mediator variable. In our running example, this was something like a network structure, right? And that mediator variable might then in turn influence an outcome Y. Right? So this is the pathway whereby treatment, right, receiving spending money makes you more likely to be friends with certain other students who may then smoke and cause you to smoke. Okay, so a direct effect that operates through this direct arrow from T to Y, and an indirect effect that operates through M here. Okay? That's defined again in terms of potential outcomes, basically corresponding to one term in which we hold the mediator fixed and vary the treatment, and another term in which we hold the treatment fixed and vary the mediator. Okay. So in a typical setup, we imagine that we observe a bunch of experimental units, a bunch of subjects, and observe these variables for each one of them. Right? So we might observe covariates, confounders, treatment, mediator, and an outcome for each observational unit. And then we estimate the average treatment effect and its decomposition into the natural direct effect and the natural indirect effect accordingly. And now this estimation is possible only under certain assumptions, right? Among those assumptions is that SUTFA assumption we just mentioned. At the risk of kind of going down too much of a detour, I'm going to kind of sweep those assumptions under the rug for now. Those of you who are familiar with causal inference, these assumptions really are, like for our setting, we're really just going to need exactly the kind of the assumptions you're used to, right? Sequential ignorability, positivity, all that kind of stuff. And I'll come back to that and talk about that briefly if there's time. But for those of you for whom like alarm bells are going off, I promised you the assumptions we need to get causal identifiability really are just the standard. Okay. So the focus of this talk is what if instead of this typical setup where we have what essentially amounts to independence among our observational units, what if these mediators are not individual variables for each subject, but instead take the form of a network? Okay, and I think this comes back and answers the question about SUTFA, right? Treatment, confounders in treatment are causally upstream of the network, right? So, right, it's not as though you have the network and then you apply a treatment and treatment can spill over. The idea here is that treatment has been applied and we observe the network downstream. Now again, presumably when you give kids allowance, they already have some friends. And so perhaps these assumptions are violated. That is not for me to say here, right? That's a conversation to have with practitioners. But I would say I believe these assumptions are pretty reasonable in the setting we're talking about. Because our confounders are things that are measured from birth essentially. Okay, so what if the mediator is a network? Basically, what happens if I change that M in that causal DAG to an A? Right, now don't read this causal DAG too closely. Those of you who are domain experts, like if you think about this too hard, you realize it's a cartoon, it doesn't make sense. Okay, but like intuitively speaking, we've replaced that mediator with a network structure. Okay, so just to fix notation, again, we have a vector of outcomes Y, one measured for each vertex in our network. For each vertex, we're going to observe covariates, the confounders C, okay, and binary treatment T. And we observe a network as encoded by an adjacency matrix. And again, just for simplicity, we're imagining that this thing is binary and symmetric, but everything I'm going to say from here on applies equally well to the more general case. Okay, and our goal now is to somehow or other, again, estimate the direct and indirect effects of treatment on outcome. Right? There's a direct effect of T on Y that operates through this arrow, and an indirect effect that is mediated by the network. Right? Yeah. 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 So yeah, remember the thing where I said don't think too hard about this causal DAG? It's a cartoon. Yeah. Yes, yes. Yep. I promise. Yeah, I promise it'll be clear in a second. Yeah. I sent these slides to my student Alex and was like, any suggestions? And he said, I think people are going to be confused by this DAG. And I said, I agree, but I don't know what else to put on this slide that won't take up 3/4 of the slide. I promise you this is going to make sense in a second. Right? This, like, I think maybe the next time I give this talk, I'll put quote marks around this DAG to be very clear. Like this is a cartoon, right? Yeah. Thanks for the question. Like to be very clear, this right now makes no sense at all in a way, right? Like if I observe C for each subject and T for each subject, and then what A is now N by N, it's weird. Right? It won't be weird in a minute. Thanks for the question. Other questions before I move on? Yeah. A is observed. A is a network, right?
Just
A is a social network. We get to measure it. Yeah. A is not latent at all.
Some random variables with each vertex or just
Yeah. So I think yeah.
random variable.
I think so. A is going to be random here, but I think so. The question was, is A latent, meaning is it unobserved? And the answer is no. Right? We're imagining that we observed a social network, like from questionnaires given to students. And then I think you're also asking, how are we going to generate A? So A is going to be random and it's going to come from somewhere. And those of you who know, like, you know, Harry Preeb's general group know that I'm going to use a random dot product graph, like a particular latent space model for networks. Yeah. Okay. By the way, I think I didn't say this at the beginning of the talk, but I usually do, that my favorite talks are ones that devolve into arguments, friendly arguments, but arguments nonetheless. So please do speak up with questions or anything like that. I won't be upset if we don't get through all the slides. Okay. So I should very briefly mention that we are not the first people to think about stuff in this vague space. Most previous approaches to these kinds of problems fall into two camps. One basically boils down to trying to predict responses based on basically your neighbors and then some additional node level covariates, things like confounders. So closest in spirit to the present work is work by my friends and colleagues Conley and Xianxi Li. Again, this set of approaches is not doing what we're doing, right? Here, basically, these approaches treat your network structure as a confounder, right? It's something you're conditioning on, which we are not doing in the present work. The other family of approaches that you'll likely see out there in the literature get more at our question about spillover effects, right? Where we imagine that there is a network that pre-exists treatment, okay? And then decisions to treat particular subjects may spill over via the social network. So this is especially shown in work by Betsy Ogburn, Ilya Spitzer, Eric Chetkin, that group. And then there's also a great paper from my academic brother, Dan Sussman, on this stuff. But again, this is different from what we're thinking about here today, right? In these works, network precedes treatment, and treatment may spill over via that network. Right? So the decision to treat you might induce a change in behavior to your friends. Okay, that is, we're reversing that causal error here today. Okay, so in this work, network structure is a mediator, meaning it is causally downstream of treatment. Okay? And I'll also point out that most of these works, especially in the peer effects and network interference literature, are assuming that a network is fixed and known. Here, we're not making that assumption. We're imagining that our network is presumably only noisily observed, right? If you ask students to list all their friends, they might forget a friend, or just, you know, maybe they're having a fight with one of their friends that week and they don't list their friend, right? The network we observe is a noisy version of some true underlying structure, and we'd like to take that into account. Okay, I'll come back to what I think is the kind of spiritually closest paper to ours near the end of the talk. That's by a group of Italian folks, and I'll talk about that work a bit more later. One other line of work you might be familiar with that's related to the present work has to do with questions of homophily and contagion in networks. And I'm sorry, I'm trying to get how do I get this guy to go away? I guess it's just stuck there. All right. So there are two different ways that you could get observations at a node level in a network. I mean, there are more than two ways, but two obvious ways. One would be something like birds of a feather flock together, right? Students who engage in the same behaviors are likely to be friends, right? You become friends with someone because you play on the same curling team. I live in Wisconsin now. I have to talk about curling. No one knows what curling is. You Google it. Right? You become friends because you're on a sports team together, or because you do the same activities, something like that. Right? So, and again, don't think too hard about this DAG, right? It's a cartoon, but roughly speaking, right, behaviors lead to network formation, right? That's homophily. In the other direction, we might see things like contagion, right? This is more like peer pressure, right? I smoke and might induce you to smoke because you're my friend. You shouldn't be friends with me if I smoke, though. Yeah. Okay. Now, interestingly, there's this great paper by Cosmas Shalizi and one of his students that says that, in fact, from observing a single network with node level covariates, it is impossible to tell these two different things apart. Right? So if you can see networks evolving over time or something like that, you can tell these two different situations apart. But if you observe just one network at one point in time, there's no way to tell the difference between homophily and contagion. There's no way to figure out the direction of this arrow. Okay. I want to stress that this talk is neither of these settings exactly, again, because the network is a mediator, not a confounder. But if you really want to put this paper into one of these two bins, so to speak, contagion is the right way to think, right? You receive a treatment, right? You are more or less likely to form friends with certain people owing to that treatment, right? And your friendships with people might influence behaviors. So this looks more like contagion if you really want to fit this into one of these two buckets, but I want to stress that the analogy doesn't quite work all the way. So just a heads up. Okay. How are we doing for time? Okay. So just to remind everyone, we have a vector of outcomes y, right? One measured at each vertex. Again, that's whether or not a student smokes. We have vertex level covariates in the form of a treatment T that is influenced by confounders C. So Ti will be a binary indicator of whether or not a student received allowance money, and Ci is this vector of confounders associated to each vertex. Okay, and then of course we observe an adjacency matrix. Okay, and now we're finally going to turn this cartoon that should have quotes around it into an actual like bona fide causal DAG. Okay, so questions on this setup before I show the kind of more detailed picture here? Lovely. Is that a question? Yeah. Yeah, so not in this project. The question was about propensity scores. Not in this project. I've been talking about that with my colleague Hyun-Sung Kang at Wisconsin. I'm happy to talk about some of that stuff offline. Yeah, not in this. This is entirely potential outcomes, no propensity scores. Sorry, other questions before I move on? Great. Oh, I'm sorry. One more, one more slide before we see the actual diagram. I apologize. So we'd like to work with this network A as a mediator, right? That's a little hard to do for at least two reasons. One, if I want to think about what happens when I intervene on this variable, right? What happens when I flip a single edge of this network? Well, changing one edge of the network changes at least two responses, okay? And making more complicated changes to the network change, well, that many more responses. If you sit down and try to do the math on that, it gets a little unpleasant. And so we decided, let's try and find some other approach, okay? Secondly, I want to point out, and like I've already kind of alluded to, the network we observe is usually not the true adjacency matrix, right? The true network is some underlying structure that we don't get to see. We see a noisy version of it. We might even see a network where some edges are missing, right? For certain pairs of students, we just don't know if they are friends or not, right? So we'd like to have some kind of a structure that accounts for that fact. And what we're going to do is model this network A as arising from some underlying low-dimensional, smooth, latent structure. Okay, those of you who like know about the random dot product graph, and folks in Maya and Jesus's area like saw this coming from a mile away, right? Those who don't, I'll talk about specifically what model we use in just a moment. But the idea is going to be that we replace A here with a low-rank structure. Okay, and that low-rank structure will play the role of mediators, but we don't get to see that low-rank structure. What we see is a noisy copy of it. Okay. So what is that low-rank structure going to be? It's going to come from the random dot product graph. This is a model for network formation, whereby latent, unobserved geometric structure drives the network. Okay. So for each vertex, we're going to have a latent position denoted by x. So the first vertex has a latent position x1, second vertex has a latent position x2, and so on. These are vectors that all live in d-dimensional space, and their inner products are going to be constrained to be between 0 and 1. And conditional on these latent positions, we'll generate edges in our network by looking at every pair of vertices, I and j, and for each pair of vertices, we look at the inner product of their two latent positions, xi and xj. We flip a coin with that probability of heads. If it lands heads, we place an edge between those two vertices. If it lands tails, we don't. Okay? Just notationally, we're going to take those n d-dimensional latent positions, collect them in the rows of a matrix X, and we'll write for short that our network A is distributed as a random dot product graph, RDPG, with latent positions X. Okay. In cartoon form, that looks something like this. We start with some latent positions here at the left. We form their gram matrix, right? We take all their inner products. And now to generate a network, we go for each pair of our vertices, say, I don't know, yellow and purple, right? We go to the yellow comma purple entry of this gram matrix. We find a probability there. We flip a coin with that probability of heads. If it lands heads, we place an edge between these two vertices. If it lands tails, we don't. Okay? Now, I'll just mention that there is a non-identifiability issue here. Namely, if you take an orthogonal transformation and apply it to every one of these latent positions, the inner products don't change. And so the distribution over networks doesn't change. So we're only going to be able to hope to recover these latent positions up to some orthogonal non-identifiability. Okay? For the purposes of this talk and basically every work ever on the random dot product graph, this non-identifiability is not an issue. The questions we tend to want to ask really don't depend on the precise orientation of these latent positions. It just depends on their relations to one another. Okay. For those of you who are familiar with the networks literature, to situate this, the stochastic block model, a very widely used famous model, is a special case of the random dot product graph, right? And the random dot product graph is a special case of the more general graphon. So the random dot product graph kind of sits between the simplicity and ease of the stochastic block model, but it doesn't have the kind of like wide open expressiveness of the graphon, which is so expressive that it's hard to estimate in some situations. It's kind of a happy medium between the two. Okay, here's that causal DAG that I promised. So with these latent positions in hand, we can now write down an actual model. So this is no longer in quotes. This is actually what we're going to do. For every vertex, we have a set of confounders Ci. Those confounders influence a treatment, which we still assume to be binary here. The confounders in the treatment both influence this latent position X, right? And the confounders treatment and this latent position all influence treatment. Okay. Now, if we could observe this Xi, everything would be great. We'd be in kind of the classical setting of causal mediation analysis. Okay? But we don't get to see these X's. We observe them only noisily through our network A. Okay, so these latent positions X would be mediators if we could see them, right? Or I guess they are mediators, and if we could see them, we'd know exactly what to do, right? But we don't get to see them. Okay, they're unobserved. So we're going to make pretty standard assumptions for this literature. For this talk, I'm just going to talk about this very simple linear model. I am very confident that this extends to GLMs, and we're working on that as extension. But let's just keep things nice and simple here. Yeah, go ahead.
What is index I stand for?
I indexes the vertices. The question was, what is I? So I is indexing the vertices here. So I ranges from say 1 to n if we have n vertices. Yeah.
Each vertex has its own observable data yi.
Yes, so an outcome yi, that's correct. So every vertex, I think the question was, so every vertex has an observation yi. We see an outcome at every vertex. But for every student in our study, we know if they smoke or not. Yeah. There's another question? Yeah. Yeah, so it's a great question. The question was like, what the heck are these things anyway? That's a great question. I think in general, right, so if what you're asking is like, is there an interpretability to these? The answer is kind of no. It's not as though the third entry of Xi encodes something specific. Pause on that until the last slide we're talking about future work. If time allows, I'll mention that. So one issue you might have with the random dot product graph is that this model basically will just pick, I mean, it amounts to doing an SVD on A, right? And whether the factors, right, roughly speaking, there's analogous to doing a factor analysis. Those factors aren't guaranteed to have any kind of interpretability. Yeah. I'll come back to that at the end of the talk if time allows, although time probably isn't going to allow, but we'll see. I'll do my best. Okay. Oh, yeah, sure. Oh, yeah. Yeah, that's the cool thing. So like, So the concern is like if these x's are only identifiable up to rotation, doesn't that make this whole model impossible to estimate? And the cool thing is that non-identifiability cancels out. So everywhere you need to estimate, right? So think of it here, like this x, right, needs to have a q in front of it to account for that non-identifiability. But this beta operates in the same space, so it gets hit with the same q.
So in theory, if you want to interpret this later on, you just have to be aware that it's on there.
Yeah, and again, I'll talk about interpretation in a minute. Yeah, or not. Well, okay. When I say talk about it, I mean I'm going to mention it as future work and why you should believe that you can do something sensible. Okay. Right. Okay. So this is our model, and I'm going to mention that, of course, we don't even, right, so this is the expectation of x. What about the x's variation about its expectation, and similarly, y, the outcome's variation? For our results, all we need is basically that these xi's are independent and have bounded second moments, right? So no distributional assumptions on x about its expectation. Similarly, no distributional assumptions about y. We basically need like sub-gamma tails on y, right? So very general in terms of the distribution of x and y about their conditional expectations. The piece of this model you might quibble with is whether the linear model here is reasonable. I share your quibble. I don't know, but this is a very standard setup in the causal mediation literature. So we're going to use it as sort of our baseline, and we have follow-up work extending this to GLMs. Under a model like this, and under suitable assumptions on those counterfactual variables I mentioned a while ago. And again, those of you who are familiar with the literature, that's things like the Sutva assumption, and then positivity, sequential ignorability, all of that. And I'll talk about that in a moment. So under this linear conditional model, under those tail-bound moment assumptions I mentioned, and under suitable standard assumptions on these counterfactual variables, the causal estimands we care about, the natural direct effect and the natural indirect effect, are identified and have this form in terms of this, the coefficients of this linear model. Okay, and the proof of this is a standard argument. Chapter 5 of van der Weel's great textbook covers this. So, as I mentioned a little while ago, if we knew the latent positions, if we magically had access to these unobserved latent variables, we'd be done, right? Like, but 10 years ago, people already figured out how to do this. Okay. But we don't see the latent mediators, right? We don't get to see those x's. We only observe them noisily through our adjacency matrix A. In the interest of time, I'm going to kind of blow by this slide. But the important takeaway is that there exist methods for estimating the x's from A. Okay? And those methods recover the true x's at a rate that's fast enough for our purposes. Okay? If you're curious, those methods include the adjacency spectral embedding by Dan Sussman and other folks from Johns Hopkins. There's also some great recent work by Fangjung Xie developing extensions to this that improve the rate a little bit. So for our purposes, suffice it to say, like, it is possible to estimate those latent positions, and to do so computationally efficiently, it just requires an SVD. And the rate at which we recover the true x's up to that non-identifiability is suitably fast for our purposes today. So our issue was that we don't have access to those latent positions x, but we can estimate x up to that non-identifiability as, say, x hat using this ASE or one of a few other methods. So if we don't know this x up here, let's take these x hats, right, for each of the true latent positions, plug in x hat for it, and let's proceed as though those x hats were the true x's, and just hope that the error between the x hats and the true x's aren't so big that they wash things out, right? Okay. Well, the nice thing is that when you do that, everything still works asymptotically. So once again, under suitable assumptions on those potential outcome variables, under this model, under suitable error bounds, tail bounds on x about its expectation and y about its expectation, right? Plugging in x hat in this regression and plugging in x hat in this regression yields some estimators for these coefficients, in particular beta t hat, beta x hat, theta t hat, and theta t c hat, such that if we plug them into the our expressions from the previous slide for estimating the natural direct effect and the natural indirect effect, these estimates are still asymptotically normal about their true targets. And furthermore, we can consistently estimate their asymptotic variances using standard techniques. So those of you who are familiar with this literature, this really is like take the sandwich estimator and just like plug in your hats. So I've been informed I have about 10 minutes. I'm going to try and finish things in less than that. And that means blowing past this non-parametric identification slide. Again, those of you who are familiar with the literature, this is really the standard, these are standard assumptions. I don't think this freaks anyone out. Happy to talk about this more offline. I'm going to blow past it in the interest of time. Let's come back to our study. So we have a social network, that's our A, constructed based on self-reported friendships. It's a noisy version of some, we hope, true underlying structure among these students, right? Certain students have latent positions, whatever those might correspond to, that are closer to one another than others. Okay, we have demographic data about these students, and then we have data about how much spending money they receive from their parents each week. Okay, and then for certain students, we observe whether or not they smoke. Okay, so here's what that network actually looks like. On the left, I have vertices colored according to tobacco usage. Notice, like I mentioned, that network is secretly under the hood directed, right? We ask each student to list their friends, and like I might list Jesus as my friend, and Jesus might not list me. Jesus is really mean to me today. I'm kidding. Right, so this is what that network looks like. These vertices are drawn size corresponding to their popularity, meaning how many people listed them as a friend. Okay, so on the left, we have tobacco usage coded by the salmon color corresponds to never smoked, and then green and blue correspond to either occasional smokers or regular smokers. I don't know what's up with 13-year-old regular smokers. That's very strange to me. But it was a different time. I don't know. Okay, and on the right, the exact same network, now with the vertices colored according to how much weekly spending money they're given by their parents. So we're going to binarize that. Happy to talk offline about, how do we pick that threshold and all that. The short answer is that that threshold was, we picked several different values. They all kind of gave us the same results. Those same results were all null results. So this data set was analyzed previously by Di Maria and co-authors using a kind of similarly flavored model to what we're doing today, is a Bayesian latent space network model, so a different network model that is still driven by latent structure. Their analysis found no average treatment effect and found that the NDE and NIE were both 0. We find the same, right? So which is a good sanity check. I also want to point out that a question I typically get when talking about the random dot product graph and related latent space models is, how do you pick the dimension D, right? So one question you might have is, does our conclusion, right? Our conclusion depends on the embedding dimension we choose, right? We get these x hats. Those x hats require us to choose an embedding dimension. We used eigenvalue cross validation, a really nice method developed 2 years ago now by Sebastian Roch and Carl Rowe at Wisconsin and a couple of their students. For what it's worth, that method on this data selected 9 dimensions, but just at the sanity check, we ran this analysis for a bunch of different latent dimensions. We find kind of the same basic result throughout. And again, these error bars are coming from that asymptotic variance estimate that I mentioned. If you're curious, I have a slide about that in my extra slides. But this comes from just plugging in those hat estimators into the sandwich estimator. Right, so again, our analysis agrees with previous analysis of this data set. Okay, I think I have about 5 minutes. I want to very quickly run through a different analysis that I think is really cool. So this data now is going to be text data. I mentioned how we can handle directed networks, right? You saw that in the previous analysis. We don't even need necessarily a network structure that is kind of nice. So this, and I'll explain what that means in a second. This is a data set collected from the OkCupid subreddit. So those of you who are familiar will know that Reddit is a forum, I guess. It has these subforums dedicated to particular topics called subreddits, right? And one of these subreddits, one of these forums is about the online dating app OkCupid. Okay, so there are about 13,000 top-level posts. So basically like comments made by users coming from about 830 individual users. So we can assemble all these posts into an incidence matrix whose rows are indexed by words, so different words in the vocabulary, right? The, a, of, you want to throw those ones out. I was a linguist once. right? But you might have things like, I don't know, date, flowers, whatever. I don't know, you have different words that index the columns, excuse me, index the rows. And then you have indexing the columns of this matrix posts. So each post the user makes, we look in the post, you see a bunch of words there. I'm going to try and gesture without moving this mic right into my face. You see a bunch of words there, you populate that column of this matrix accordingly. So the treatment exposure we're interested in here is a user supplied flare. So users on Reddit can select a flare, like a little badge that shows up next to their username. On this forum, it is popular to choose that flare to indicate your sex, male or female. We're using that as our treatment here. And then the outcome here is going to be the net upvotes, basically the difference between how many people liked the post and how many people disliked the post. Okay. So I want to point out this data is still a matrix, right? It's still an adjacency matrix-like thing, but it's no longer a symmetric adjacency matrix. In fact, the best way to think about this is as a bipartite network, right? Where one part is posts and another part is words. And there are edges from posts to words corresponding to whether that word appears in the post. And so now we have a network with two parts, a bipartite network, and we have a treatment that was applied only to one of the two parts, right? This flare only makes sense for the posts, right? Each post has a user who has a flare, right? Words don't have flares. So sad. Okay. But we can still construct embeddings of these posts, right? Of these top level posts, there it is, right? By looking at the right singular vectors of this word post incidence matrix. Okay. So we can build that embedding and then run right on ahead and run our analysis the same way as we outlined before for the latent positions of a network. I want to point out that this a similar analysis was run previously by David Bly and some of his group. In that approach, the mediators here were neural net embeddings. So instead of trying to build these embeddings into an end-to-end model, they're trying to learn embeddings using a neural net. The problem there is that then when you want to build confidence intervals for the natural direct effect and the natural indirect effect, they basically have to resort to resampling data. And the confidence intervals they get are suspiciously narrow, right? And because it's expensive to run this whole machinery, they only get 10 resamples of these things. Okay? So an advantage here is that we have the same kind of philosophical approach, but because we have kind of an end-to-end model, our resulting confidence intervals on these things look pretty reasonable. One thing I want to point out that as we increase the embedding dimension, so again, this is the same plot you saw a couple of slides ago for a different estimand. Right, x-axis is our embedding dimension, and one thing I want to point out is that our estimated indirect effect goes from 0, up to a steady state or down to a steady state of about -0.5 as we increase that latent dimension. So what's happening here? The average treatment effect is a number; it is fixed, right? ATE equals NDE plus NIE. So if we embed into too low a dimension here, we're failing to capture all of the network structure that's present, and therefore we're underestimating the indirect effect, and we end up overestimating the direct effect to compensate. Okay, in sign, like in magnitude, not in sign. Right? Okay, but once we choose this embedding dimension suitably large, things are stable and really insensitive to the exact choice of embedding dimension. Right? Once we've captured all of the low rank structure that's present, we're kind of free to just keep increasing D if we felt like it. I think I said all this, right? And I'll also point out the estimates we end up with are compatible with previous analyses. It's just that I would say that these confidence intervals are a lot more believable. Okay, so I think we're ending right about on time. Yeah, just about. So just to recap, what did we do today? We set up a problem where it was sensible to think of network structure as serving as a mediator in an observational data set. We showed how well, working with that network directly is a little hard, but what if we think of that network as being a noisy version of some low dimensional structure? We then use that low dimensional structure as our mediator, and out the other end of that machinery, we get estimators for the natural direct effect, natural indirect effect, and while I didn't mention it, we also get an estimator for the conditional direct effect under this kind of network mediation. Okay, and we also proved on the theory side that we have consistent and asymptotically normal estimates. Very, very quickly, I want to mention some future directions. First and foremost, to come back to that interpretability question. So One different way you could build these embeddings is using something called the Baramax embedding. This is recent work by my colleague Carl Rowe and his student Mujie Zheng. The nice thing about these is that they are approximately sparse, right? That like basically each entry of your embedding now at least corresponds to a pretty like pure cluster, we call it in the clustering literature. Okay, so there's a hope that that gives you more interpretable embeddings. You can look at the resulting embeddings and kind of cross-check them against other information. Things like on Twitter, you can look at who posts about what, and typically these Baramax embeddings really do correspond to communities on Twitter. I'm happy to talk about some of that more offline. And in fact, my student Alex Hayes can tell you even more than I can. I think one other interesting thing to think about would be using this latent space embedding to model a contagion or diffusion process, which kind of gets back at that distinction I mentioned between homophily and contagion. So I think I'm going to leave it there. I will thank you all again for your time and attention, and I'll be happy to answer any questions. Thanks so much.
How exactly you balance these types of random graphs in the case refactor arguments? Because in the untractor case, you have the metric operation in our
Yeah, so here basically the model that you use. So the question was about how do you model this directedness? So when you have a directed network now, you don't have the same left and right eigenvectors, right? That could serve as a kind of natural way to build an embedding. You have left singular vectors and right singular vectors, and we just stack those. Really straightforward. Yeah. And the model ends up being again like inner products between the left singular, or excuse me, an edge from I to j has probability given by the left singular vector of I inner product with the right singular vector of j. You just draw out the you probably get it, but right, u v whoops, oh my gosh, u lambda v transpose, right? The ij entry of this thing is like ui, ignoring the okay, there. My v's and u's look identical. Yeah, there's a lambda in there. I'm ignoring it. Please. Oh, he's ready to show.
First example. In the first example, you said T influences M, but it seems for that example, that your N may also influence T. The mediator.
Yeah. So let's go way back here. Yeah. So the question is about oh geez, oh that's too far. Where did it go? Let's just use this. Well. Okay, let's use our bad cartoon that I warned you all not to think too hard about, but it's useful here. Okay, so I think the concern is, so we have some covariates and like demographic information. We have treatment, like did a student receive a lot of spending money or not from their parents, and then we observe a network. And the concern is that maybe this model is incorrect. Maybe in fact, maybe my parents give me $20 a week and your parents give you 50, and so I go to my parents and I'm like, come on. Like Joey over here gets $50 a week and I'm getting 20, this isn't fair, right? So yeah, that's possible, right? So I said a couple of times during this talk, like there's a separate question of, do you believe this causal DAG? That's for your collaborator or you to decide, right? I think this is reasonable. My personal opinion is that this is reasonable for this data set, right? Like, yeah, actually we've got some of that in the paper. Happy to talk about that more, yeah.
I have a follow-up question
Yeah.
on that. So you calculate from variable from the changing habits and also how they spend their leisure. So I was wondering, where do they come? Because they can't be the like the C, because you are.
I'm really sorry, I didn't quite catch the first half of
Yes,
the.
you are collecting some data on the variables such as like how do they spend their leisure and their spending habits. So I was wondering that they cannot be part of C because you observed them after the treatment. So what did you do with those variables?
So in the analysis I showed you, we only included sex, I believe. I'd have to go back to the paper to double check. But you can include them. And again, that's so the question is about, we have these other pieces of information about the students, right? This kind of other information like leisure activities, sex and age, things like that. And the question is, can you really include these, say, leisure activities as a confounder, right? If it is the case that in fact, maybe they're downstream of the network, or maybe they're measured after the fact. So whether they're measured after the fact, I don't think is such a problem. The question is whether they are causally upstream, right? So I suppose the assumption you're making, if you include those leisure activities in this model, is you're assuming something like this student says they play soccer, and the fact they say that now, they were probably also playing soccer before, you know, the experiment ran, something like that.
But if you include them as mediators, then you are targeting to start probably. That's why
You include the sorry, if you include the, so if you include these as mediators, is what you're suggesting?
Yeah.
So basically you're saying, you're asking, could you, maybe I'm not getting the question correctly. Are you asking like, could I add, you know, also?
It's not straightforward how to add, but I was wondering if apart from
I think it is. So your question is, could I add an additional mediator variable here? Yeah, absolutely, right? You basically just be stacking those covariates with the x's, with the latent positions, right?
X is you don't observe it.
X we don't observe, but the fact that we can estimate it from, so the concern here is that, but X is not observed and the covariates are, these maybe covariate mediators are observed, but it's okay. It's like, think of it like errors in variables, except the error in the variables is shrinking to 0 as you get a bigger network. Yeah.
That's our,
Thank you all so much. Really appreciate it.